In this lesson, we're going to be looking at right and left-hand limits. So if you see a plus after the value, that means from the right or positive side. So this is the limit of x minus 2 divided by x squared minus 4 as x approaches 2 from the right-hand side. So as x approaches 2 from the right, in other words, values that are a little bit larger than 2, what value is y approaching? So let's see what's happening. Right, so when x is 2.2, f of x is 0.2381. When x is 2.1, our function is 0.2439. When x is 2.01, the value of the function is 0.2494. Look what's happening. Right? So as x is getting closer and closer to 2, our function is getting closer and closer to 0.25. The function doesn't exist itself at 2, so f of 2 does not exist. However, the limit of x minus 2 divided by x squared minus 4 as x approaches 2 from the right-hand side exists, and that value appears to be 0.25. Let's look at the left-hand limit. If you see a negative after the value, that means from the left or negative side. So we have the limit of x minus 2 divided by x squared minus 4 as x approaches 2 from the left. Let's look at the table. Right? So we're looking at values of x that are a little bit smaller than 2. And we're looking at what y is approaching. Right? So we have x is 1.8 and the value of the function is 0.2632. When x is 1.9, f of x is 0.2564. When x is 1.99, f of x is 0.2506. So notice our function is getting closer and closer to 0.25 when x gets closer and closer to 2 from the left-hand side. So the limit of x minus 2 divided by x squared minus 4 as x approaches 2 from the left is equal to 0.25. So both the left and the right-hand limits are the same real number. Therefore, the limit exists, and we can then conclude that the limit of x minus 2 divided by x squared minus 4 as x approaches 2 is equal to 0.25. And so let's take a look at this graphically so this will make sense. Right? So our function was y equals x minus 2 divided by x squared minus 4. That's equivalent to y equals x minus 2 divided by x minus 2 times x plus 2. We could factor that x squared minus 4. Notice that we could cancel those x minus 2's. So now we could rewrite this as y equals 1 divided by x plus 2, provided that x does not equal 2. Right? Because if we plug 2 into the original function, right, we're going to get a 0 in the denominator. All right, so let's graph this function, y equals 1 divided by x plus 2, provided that x is not equal to 2. We have a vertical asymptote. Right? If we tried to plug in negative 2, we're going to have 1 divided by 0. Right? So we have a vertical asymptote right here at negative 2. What happens at positive 2? Right? Well, if I plug in positive 2, I have 1 divided by 2 plus 2. So that's 1 divided by 4, 1/4. Well, 1/4, that's the same as 0.25. So notice our function doesn't exist at 2, but we do have a hole here at 2, 0.25. We'll just graph some values of our function on the right-hand side of that vertical asymptote, since we were interested at what's happening when x is 2. Right, so I'll plug in a couple values. So for instance, if x were 0, right, the function would be 1/2. Right? If x was negative 1, right, I'd have negative 1 plus 2 is 1. Right? So that's going to be 1. Right? So we have this vertical asymptote here, so we're not going to cross that. So here comes our function from the left-hand side. From the right-hand side, these values are going to get smaller and smaller, right? If I plug in larger and larger values of x, right, I'm dividing 1 by larger and larger values, I'm going to get smaller and smaller. I'm not going to be negative, right? I could plug in 100, right? And I'd have 1 over 102, not negative, but smaller. So notice that from the left-hand side and the right-hand side, our function is approaching the same value. And so even though the function doesn't exist at 2, the limit exists at 2. So the limit of x minus 2 divided by x squared minus 4 as x approaches 2. X approaches 2 exists, right? And that value is 0.25 because we have the same value, we're approaching the same value from the left-hand side and from the right-hand side. And that supports what we just saw in the tables. Let's look at right and left-hand limits in a little more detail. If we're concerned with the limit of f of x as we approach some value c from the left-hand side, we're going to write the limit of f of x as x approaches c. That negative means the left-hand side. If we're concerned with the limit of f of x as we approach some value c from the right-hand side, we're going to write the limit of the function as x approaches c, and we're going to put a plus there for the positive side. Make sure you fill that in your notes. Make sure wherever I'm writing stuff, you're writing stuff. Because if I wrote it down and it's space in your notes, it's got to be important. All right, so let's look at a little more detail at left-hand limit and right-hand limit. So if the value of f of x approaches a unique number, L subscript 1, as x approaches c from the left, then the limit of f of x as x approaches c from the left is L subscript 1. Right? So that negative just means that you're approaching from the left. Right? So we can have a left-hand limit. We can have a right-hand limit. If the value of f of x approaches a unique number, L subscript 2 as x approaches c from the right, then the limit of f of x as x approaches c from the right is L subscript 2. Right? So we can have a left-hand limit. We can have a right-hand limit. Let's look at this one, and this one is a left-hand limit. And my negative is very hard to see, so I'm going to make that a little darker. All right, so we have a table here. Since this is a left-hand limit, we're going to look at values that are slightly to the left of x equals 3. All right, so we've got some values of x we've plugged in. If x is 2, f of x is negative 2. If x is 2.9, f of x is negative 29. If x is 2.99, f of x is negative 299. If f of x is 2.99, f of x is negative 2,999. Are we approaching some value? Are we getting closer and closer to some value? Well, it looks like the numbers are just getting smaller and smaller and smaller. Or you can think of them as getting bigger and bigger and bigger, but in a negative direction. So our limit as x approaches, the limit of x divided by x minus 3 as x approaches 3 from the left, since our values are decreasing without bounds, is equal to negative infinity. Now, does this mean the limit exists? Does this mean the limit exists? You write that question in. Does this mean that the limit exists? And actually, I should say the left-hand limit, since we're only looking at a left-hand limit. That the left-hand limit exists. Let's go back to our definition on the previous page. All right, so left-hand limit as the value, if the value of f of x approaches a unique number, is negative infinity a number? Well, no, right? You can't give me negative infinity apples or something, right? It's not a number. It's just telling us that it's decreasing without bounds. So we can, and we should write negative infinity. That tells us, you know, what's happening, that we're decreasing without bounds. But does this mean that the left-hand limit exists? No, right? our function here, f of x, is not approaching a finite number as x approaches 3 from the left-hand side. Okay, so technically, our limit does not exist. We have to approach a finite number. Negative infinity doesn't count as a finite number. It's the opposite. All right, so one and two-sided limits and existence of limits. So when we see the limit as x approaches a, that's a two-sided limit operator in the limit of f of x as x approaches a, because we have to consider the behavior of f as x approaches a from both the left and the right. Right? When we're just looking at whether the limit exists, right, we were looking at what happens from the left-hand side, what happens from the right-hand side. When we see a limit as x approaches a with that negative, that's a one-sided left-hand operator. Right? So that's the limit of f of x as x approaches a from the left. The limit, when we see the positive, so the limit as x approaches a with the plus sign, that's a one-sided right-hand limit operator. And that would be the limit of f of x as x approaches a from the right. So the limit of f of x as x approaches a is only going to be equal to L if the limit of f of x as x approaches a from the left-hand side is L, and the limit of f of x as x approaches a from the right-hand side is L. And not only that, so we see A and L, and that funny looking E and the R there, that's written in lines that aren't colored in. What does that all mean? Right, so A, that's that value there, right? And L, that's that value there. This here, and I don't draw that very well. Mine looks like an E. I have a hardest time drawing this one. Yeah, that looks better. That means is an element of. They come up in a moment. There we go. Is an element of. Right? So A, the value x is approaching, and L have to be elements of, and that let's see if I can draw that. Oh, you say no. Here, we'll draw it like that. That's another way you can write it. That means real number. All right, in your notes, you can make it look prettier. All right, so in the case back over here, that's not a real number. Right? Our limit is not a real number. Right? So that left-hand limit does not exist. Right? So it has to, not only do they have to be the same value, the limit has to be a real number. Right? So a two-sided limit exists if and only if the corresponding left-hand and right-hand limits exist and they're equal. If either one-sided limit does not exist, or if the two one-sided limits are unequal, they're not the same value, then the two-sided limit does not exist. Right? So your right-hand limit has to exist and your left-hand limit has to exist, and they have to be equal to the exact same finite number. And if that's not the case, your limit does not exist. Right? So here's a little visual for you, help you out. In order for a limit to exist at C, the limit of f of x as x approaches C from the right-hand side has to equal the limit of f of x as x approaches C from the left-hand side. And the limit has to be a real number, right? As we saw in the last slide. I'm going to end this podcast now, In the next portion, we're going to be looking at some more numeric limits, and we're going to be looking at some that may or may not exist. Bye for now.